Brayden, waiting on you. Is it possible to join a Kahoot after it begins? All right. I don't know if you can hear me, but I'm just gonna get started. All right, first question we already know the answer to. Yeah. I mean, I can just skip. Yeah. So interstellar cloud. All right, please. Next. All right. The stages of star formation are based on this property. All right, all 5 answers. You guys are right. This Kahoot is wrong. It's not based on temperature. It's based on mass. Yeah. Again, I'm not making this Kahoots because it takes a really long time to make a Kahoot, because I have to think of like wrong answers, and to think of wrong answers is very difficult. But you guys are right. It is mass that determines it, because the bigger a star is, of course, the hotter the star becomes, right? This is something that I've taught you guys. So you guys are correct. The Kahoot is wrong. A failed star which isn't hot enough to start nuclear fusion is known as what kind of star? All right. So a neutron star is that does not fuse. That is correct. But the thing is, the neutron star already is a remnant of a star, right? All right, so Yinghua, we are currently in a Kahoot. There's the game pin on the bottom. But I was just talking about the current question, which was a failed star which isn't hot enough to start fusion is known as a brown dwarf. So a brown dwarf is, it was a protostar, and then it didn't get enough mass to start fusing. A neutron star did at one point have enough mass, right? It was a main sequence star. It became a red giant and then underwent a supernova and then became a neutron star. But it was not a failed star. It was a star at one point. All right. When the energy released is balanced with a force due to gravity, it's known as, I'll put the code for the Kahoot back into the chat one more time. Yeah, as equilibrium. So this is that really fancy term that I'm just going to pull it out, that we talked about in the very beginning. I think it's called stars, right? When we're talking about what happens inside the core of the sun, right? We call this really fancy term, self-correcting hydrostatic equilibrium, right? Because when the core and gravity are all balanced together, that's what we call equilibrium. All right. After a star runs out of hydrogen, the core shrinks and begins to fuse. Think, what atom comes after hydrogen? Right. So the correct answer here is helium because helium comes directly after hydrogen on the periodic table, right? Because when you fuse two hydrogen atoms together, you get a helium. You fuse two helium atoms together, you get a carbon, and you get fused carbon to get neon, and neon to get silicon. So all of these answers are things that stars can fuse. However, once a star stops fusing hydrogen, it immediately begins to fuse helium right afterwards. So helium is the most correct answer here. All right, a fourth of the way done. So once a star begins to fuse helium, what stage is it in right now? So yeah, should be a giant. Because remember, when a star is in its main sequence form, that's when it's fusing hydrogen, right? It's fusing hydrogen, fusing hydrogen, fusing hydrogen until it runs out of hydrogen and it can't burn anymore, can't fuse anymore, and therefore it's kind of swells, the core collapses, and it burns brighter, and that means
I see you talking, but you're on mute.
thank you. Yeah, I'm not sure what happened, but yeah, thank you for that. What I was saying was that low mass red giants, the key word here is that they're low mass, right? And low mass stars can only fuse hydrogen mostly. Since they can only fuse hydrogen, when they reach a red giant phase and try to fuse helium, they can only do it somewhat. They can't really fuse heavier elements. So as it runs out of helium, then no more fusion happens, and therefore the outer layers of the star drift away as a nebula, right? And the center of the star, the core, is what we call our white dwarf. So yeah, a brown dwarf, remember, is what happens is that's a failed star, right? That's a protostar that never became main sequence. So that's the difference. White dwarf is a hot center of a star, and brown dwarf is a failed star. The white dwarf will energize the surrounding gas, creating a. So I mentioned that in the last question. After those layers begin to disperse into space, it should create a planetary nebula, right? After all those layers of the star, all the gas, when there's no more fusion happening, it just diffuses into space, and that's what we call a planetary nebula. And at the center of that planetary nebula is the white dwarf. And that white dwarf is still really bright, right? So it's so super bright. So it's still shining a lot of light and lighting up all the gases that just flew away. And that's what we call a planetary nebula. Heaviest element that can be fused. All right. Yeah, so the heaviest element is iron. So I did mention this briefly, but didn't go in a lot of detail. But what I did say was that iron is one of the most stable elements in the universe. Stable because if you want to fuse iron into something heavier, it actually requires a lot more energy than you get out. So it's basically not worth the energy to try to fuse iron. So that's why stars can't really fuse iron at all. It's just too stable to do so. Neon, however, is less stable than it, and you can still fuse neon because it's a lighter element than iron. Heavier elements than iron are created during these events. So I actually did not go over this before. So take an educated guess. Almost, yeah. So of course, so we know that we cannot fuse elements greater than iron. You can't fuse those things. So instead, what happens is that in super giant stars, like supermassive stars, right, as they undergo a supernova, what happens is, the core hits iron and stops fusing. And once the core stops fusing, that equilibrium is broken, right? Then there's no more fusing force pushing out against the force of gravity trying to collapse the star in. And so with no more fusion, the star begins to collapse in on itself like that. And as it collapses, it forces all these molecules, these atoms, closer and closer together. And it forces them to fuse under the force of gravity. So they're not fusing because it's super hot. They're fusing because gravity is causing it to collapse together. So in that supernova, that really chaotic event, that's where these heavier elements in iron are created. So, the reason why we have super heavy elements on Earth, why do we have stuff like titanium? Why do we have stuff like, lead, right? All these different materials on Earth. The reason for that is because the sun actually is what we call a population 2 star. A population 2 meaning that it's like the child of a population 1 star, meaning that another really big star had a supernova and exploded and created this cloud of gas. And from that cloud of gas, it created a protostar, which became our sun. So all that really heavy element stuff that came from that population 1 star supernova is actually found on Earth. So that's how we know that the sun is not a very old star. It's population 2. All right. So this I also touched on very briefly. The Chan-Bashar limit. Just give you some context. What this is how heavy a white, so close, yeah. We're kind of split between 1.3 and 1.4. Yeah, so if a white dwarf is heavier than 1.4 times the mass of the sun, then it will collapse into a neutron star. It will surpass electron degeneracy, which is what holds it as a white dwarf, and collapse further into a neutron star, where the atoms and where the protons and electrons actually combine together to form neutrons. If a white dwarf is too heavy. How I know that it's 1.4, not 1.3, is I just think 1.4 is a nicer number. 14 versus 13, it's even. 2 times 7, I don't know. That's how I remember it. It's just nicer. All right, halfway through. A stellar remnant has a mass of 1.2 solar masses. So remember, this is below the Chandrasekhar limit. If it's below that limit, what must it be? Yeah, so below the limit means that you are a white dwarf. If you go above it, it becomes so massive, you're so big that it collapses even further into a neutron star. So if you're under 1.2 solar masses, you remain a white dwarf. Above it, neutron star. A high mass remnant that isn't massive enough to form a black hole. The keyword here is high mass, so this has to come from a supernova. If it doesn't form a black hole, what does it form? Yeah. It's not, if it's high mass, that means that it was made in sequence. It became a red supergiant, so really big red giant, and then it underwent a supernova, and after the supernova, it became a neutron star. Right, so high mass stars always end up as either a neutron star or a black hole. So if it's not a black hole, it's a neutron star. All right. A type of really strong field. Give you a hint, it's inside the name. It's in the name. And in the name as well, magnetar, magnetism, right? So, yeah, so it should be magnetar. So magnetar is a type of neutron star with really strong magnetic fields. Yeah, again, I only touched on this very briefly. So, yeah. Oh, the distorted space around a black hole. This is a very bad question, so take your best guess. Yeah, so the space around like an ergosphere is so how a black hole is like, it's a singularity, right? It means there's a point in space with a really concentrated mass, right? Imagine a whole star collapse into a single point, right? That's a singularity in the center of a black hole. And the gravity in a black hole is so strong that it pulls, nothing can escape, even light, right? If light tried to escape a black hole, it can't. It just forced back down into the black hole. So that's the singularity. And there's a sphere around the black hole known as the event horizon, which is where light can escape. If you are a certain distance away from a black hole, you're able to escape. And that is known as the event horizon. The ergosphere is a bit bigger than the event horizon, which is where you have what we call like gravitational like lensing and whatever, just like basically light that's looped around the black hole, and light is orbiting the black hole, and that's what's the ergosphere is called. And then the accretion disk is all the mass that is surrounding the black hole. So if you had a black hole and then something was swirling around it, that is the accretion disk. So yeah, this is really kind of a tricky question because black holes are really, there's a lot to know about them. So yeah, a very difficult question, a very difficult topic. I probably didn't do a very good job explaining it, but I do encourage, if you're interested, to explore on your own. So so a quasar is a type of black hole. A quasar is a black hole that is shooting out emission rays, like inside, a protostar, how it shoots out these rays from its poles. That's what is happening in a supermassive black hole as well. Those are known as quasars. So yeah, also another black hole subject, very difficult. All right, 6 more left. So this is also, I didn't go over this at all. So do your best guess. All right, so yeah, there's no way you could have known, but basically a Schwarzschild, you'll see the term Schwarzschild a lot. What that means is, of course, non-spinning. So a Schwarzschild black hole is the simplest black hole possible. It's non-spinning, it doesn't have a charge, it's a point in space, it's spherical, it's everything. It's like the perfect black hole. And a Kerr black hole is when it begins to spin. When a black hole spins, then some other crazier stuff happens. So Schwarzschild is non-spinning. All right, 5 more. Yeah, so the stuff swirling around the black hole, like that. That's what we're talking about here. Yeah, so that is the accretion disk. Yeah, as we got from last 2 questions. 4 more left. White dwarfs can steal matter from a companion star. So I guess this is also something I did not talk about. But there's something known as what we call a binary star system. Binary meaning that there are two stars in a system and they are orbiting each other like this, right? And if, let's say, one of our stars, let's say my right hand here, is a white dwarf, right? Let's make it this cube, right? This is a white dwarf. And since its white dwarf is really, really dense, it really has this really strong gravity, right? Sometimes matter from this star over here will get sucked in. So it gets sucked in as they're orbiting each other, and it'll suck in matter like that. And that is what we call a binary star system with a white dwarf in it. And as a result, sometimes that white dwarf will steal matter away from its companion. So it is possible. But yeah, again, I didn't talk about this at all. So yeah, so high mass remnants. Remember, we talked about them. Yeah, so high mass is neutron star in a black hole. So it's good that we chose at least black holes. So we know that black holes come from high mass remnants. But neutron stars are a lot heavier than white dwarfs, right? Because you have to exceed the Chandrasekhar limit to become a neutron star. And if you're below that limit, you're a white dwarf. So it's neutron star and black hole, which are high mass remnants. Brody sense black heavy. I'm lagging. Yeah, that's my bad. My Wi-Fi is not doing well. All right, does this show up? Dang it, I was muted again. Okay. All right, so can you guys hear me now? Yeah. All right, so today we're going to go over cosmology, which is the Big Bang Theory mostly. And then we're going to go over do you guys hear an echo? All right. Hello. I'm hearing myself echoing. All right. If you guys don't hear an echo, then that's fine. So I'm going to go over the Big Bang Theory, which is a theory of how everything in the universe came to be. And then we're going to talk about the cosmic microwave background and some cool stuff like dark matter and dark energy. All right. So there's a question to you guys. Where did everything in the universe come from? Any thoughts? Anyone?
Well, the Big Bang Theory says that everything came from like a super small point.
All right. Yeah. So yeah, that's what the, hold on. I'll mute. There. Now no more echo. So yeah, Brayden, you're right, that the Big Bang Theory says that everything ever in the universe came from a single point, right? Everything would kind of expanded and just boom, exploded into existence, right? But that's true. That's really good summary of it. So here is kind of a graphic of what's going on. So everything, so we're right here in space. We're currently on this edge. And if you go backwards in time, that's how you can figure this out. So scientists believe that at some point, everything in our universe came from a single point, like a dot, right? A singularity, a point in space, a zero-dimensional point, right? That's what a singularity means. And how do we even come to such a conclusion? Right? How do we figure that out? So basically, scientists are very smart. Physicists are very smart. They figured out how to describe our universe using equations, right? And these equations are known as, we call it general relativity, or known as special relativity and stuff like that. And these equations, you can plug stuff into it. So for example, if I threw a baseball, right? You can plug all the information of the baseball into these equations, like its speed, its mass, its initial direction, and stuff, and you're able to figure out exactly where the ball is going to land, even before it landed. So you're able to make predictions about the future. What scientists did is that they plugged in our current state of the universe, but put it backwards in time, basically. Imagine that baseball, it's in midair, right? And if you said, okay, how did that baseball get there? You look at its current space, its mass, its speed, and basically make it go back in time. Then you're able to figure out, oh, it came from Clark's hand over here, right? So that's a very simplified example of what scientists did. They plugged in all the energy in the universe, all the mass, everything, and put it backwards through their equations. And they found that everything at one point came from a single point, a singularity in space. And we know that that's about 1.8 billion years. So this graphic still says 1.77 because it's a bit old. Recently, within the last few years, scientists redid their calculations and found that the universe is actually a bit older than we thought it was. So it's 1.8 billion years. So now what I'm going to go through is kind of go through each of these little slices of the universe and kind of explain how did the universe come to be. So the very earliest that we know about our universe is what we know as the Planck epoch. So the Planck epoch is named after a guy whose last name was Planck, and it's named the Planck epoch because that we know about our universe. All of our equations all work up until 10 to the negative 32 seconds after the Big Bang. So the Big Bang happened at time equals 0. And then the Planck epoch is everything between time equals 0 and 0.00000 43 zeros and then a 1. 43 zeros. So everything between that and Planck, what we know, this is called Planck time, 10 times the negative 43. Everything before then, we have no idea what happened. Our equations of physics completely break down. We have no way to describe what happened up to then. And the reason why we aren't able to is because everything was just energy. everything was incredibly hot, like unbelievably hot. We're talking quadrillions of degrees Celsius. That's just enough temperatures, insane amount of energy, just pure energy. And all of the forces, like for example, gravity, magnetism, or called the strong and weak forces, all the fundamental forces in the universes were combined into a single force, because that's just how powerful and hot that time was. So that's the Planck epoch. We have no idea what happens during it. And that's how hot it is, 10 to the 32 Celsius. That's a 1 with 32 zeros after it. That's how hot it is. But we have no idea what happens before, because we have no physics to describe it with. But right afterwards, from T equals 10 to the negative 43 to T equals 10 to the negative 36, that's what we know as what we call the grand unification epoch. So you can see our temperature has cooled down a little bit. We lost 3 zeros of magnitude in the temperature. And this is grand unification, is because forces that we can determine, that we know of today, such as gravity and magnetism, have begin to separate from one another. They're no longer just one force, they're begin to separate. And how scientists like to describe this is what they call phase transitions. The same way like water, right? In water, you undergo phase transitions. So this is 0 degrees, and this is let's say 200 degrees, right? And this is maybe negative 30 degrees. This is Celsius. So water up until 0 degrees Celsius is ice, right? And up until 100 degrees is liquid, and then up until here is water vapor. If it evaporates, it becomes water vapor. And this is solid, that's liquid, and that's gas, right? So water has its own phase transitions, right? So what scientists believe is that forces also have phase transitions. So when it was super hot, when it was 10 to the 32 degrees Celsius, then all the forces were kind of in this gaseous where they all combined together. But as it dropped down and became a little bit colder, then the forces began to separate from one another. So this is the first time when gravity, it became separated, basically. Gravity started separating apart. So it underwent a phase transition. After these forces began to separate from each other, that's when the universe actually expands. So if you see in this graphic, right, you see this, and you see how this has this little shape like that in the beginning. It doesn't just immediately explode like this. This is those few, the Planck epoch and the grand unification epoch. So that happened right there. And now we hit the expansion part. This is the inflationary epoch. So this happens a little bit later. So time up to 10 to the negative 32 seconds. So T equals temperature is yet again cooled down again, has lost 10 degrees of magnitude of cooling. And up until 10 to the negative 32 seconds, the universe suddenly expands. And how much is its previous volume? So what does that look like? So if something in the universe that was previously 1 nanometer long, which is the width of DNA, right? Can you imagine? DNA is something you can't even see, right? That's inside your cells. That's what makes up you. That is expanded to 1.6 light years, right? That is, I can't even imagine, but that's how powerful that expansion was. 1 nanometer becomes 10.6 light years. So that's the expansion, basically the universe, boom, pops into existence. That's what happens in the inflationary epoch. And also during the inflationary epoch, the strong force separates. So the strong force is what holds particles together, is what holds things together. So inside even a proton is made of what we call quarks. And what holds the proton together is the strong force, or a neutron together, or the electron. That's what the strong force dictates. So since the strong force is now separated away, underwent a phase transition, particles are now able to begin forming. The next phase is what we call the electroweak epoch. So a lot more time has passed now. So this is T equals 10 to the negative 12 seconds. And now temperature is now also lost. We lost 7 degrees of magnitude on the temperature. And because it's yet again a lot cooler. You know, when I mentioned particles begin forming in the last slide, these particles formed, but they don't have mass yet. These particles are what we call force carriers. Force carriers, well, obviously they carry out forces. So the two big forces we have are the electroweak force, the strong force, and gravity. So these are our 3 forces right now. And the reason why none of these particles have mass is because the particles that carry out the weak force, known as the W bosons, there are 4 types of W bosons, the 1, 2, 3, and 4 bosons. And then we have the Higgs force. So obviously these are all really like fancy. I know I haven't really explained anything at all, but just kind of bear with me here. So there's also this thing called the Higgs force, which determines how massive something is. And since these two things haven't interacted yet, the weak force, which dictates how particles move, and the Higgs force, which gives particles mass, if they haven't interacted, then particles are not yet able to have mass. So that's basically what's happening in the electroweak epoch. When you begin to have these two forces, the electroweak force and the Higgs force, start to interact and start to give particles mass. And currently, just for scale, the universe is currently 300 light seconds wide. So everything that our universe, like everything in the universe, once was 300 light seconds wide. What is a light second? That means that if light were to travel for 300 seconds, the distance that it travels in those 300 seconds is the distance. That's 300 light seconds. So it would only take light 300 seconds to get from one edge of the universe to the other. Think about that. That's barely 5 minutes to travel the whole universe. Right? I can get to like Starbucks in 5 minutes. Right? That's a really small distance. But of course, it continues to expand. So in the next epoch is when nucleosynthesis. So you see now time is 1,000 seconds, right? Compare it to the time before. This is 10 to the negative 12 seconds. That's a 0 with 12 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1. That's a really small time. And now up to 100 seconds. Oh, sorry, 1,000 seconds, right? A lot of time has now passed. And what's been going on in between that time is that particles gain mass. The W bosons and the Higgs field have come together and they have created what we call the Higgs boson and the W, like 1 and W, I think it's plus minus. Yeah, it's W plus and W minus bosons. So you no longer have this 1, 2, 3, 4 and a plus minus 0, 0 prime. You have these, they've interacted and created these 3 particles instead. And these 3 particles are what give things mass. So particles gain mass. And since particles have now gained mass, they're able to form matter as we know it. We're able to form protons, we're able to form neutrons, and we form like the most basic atomic nuclei, like hydrogen, able to form helium, right? So that's what we call nucleosynthesis. Nucleosynthesis meaning nuclear production, basically. So like nuclear meaning, atoms. So atoms are beginning to form. That is nucleosynthesis. At our current place in the universe, after 1,000 seconds have passed, the universe has expanded to 300 light years across. So now light, if you want to travel from one edge of the universe to the other, then light would take 300 years to do that. So you see how much the universe has expanded from 300 light seconds to 300 light years in just 1,000 seconds. That's pretty crazy. Then at the next stage of the universe is what we call the cosmic microwave background. So every time before this cosmic microwave background, the whole universe is very dark. Why would it be dark? I thought you guys, you might be thinking, right? It's super hot, right? You would think, with so much light and start with so much energy and heat, that would be super, super bright, right? But the issue is that when you have so much stuff, right, so much matter all stuck together, light actually isn't able to pass through it. If you try to look at the universe back then, you won't be able to see a thing because light isn't able to move anywhere. It's like if you shine light at a wall and you try to look through it, right? That's impossible. You can't go through it. It's opaque. The universe is opaque up until then. It's just so dense. So that's what we call the dark ages. But after this, light is after 370,000 years. So after the Big Bang, after the universe exploded into existence, this is what we call the recombination. So this is recombination is, remember all those nuclei, those helium atoms, those hydrogen atoms that you created. They aren't complete, fully fledged atoms yet. The reason for that is because atoms have electrons on them, right? You have your nuclei and then you have your electron orbiting around it, right? Back before recombination, you only had the nuclei. You didn't have the electrons circling around it. At 370,000 years, recombination occurs and electrons are attached to these nuclei, creating fully fledged atoms, not just the nuclei. And when these atoms were combined onto these atoms to form full, complete atoms, it releases a lot of light. Because electrons like to be next to atoms. Before, the reason why they couldn't be next to atoms because there's so much energy going on, right? There's still 10 to the 7th degree Celsius, where it's still super hot. And these electrons don't want to be stuck on an atom. They want to be flying everywhere. And now, since it's already cooled down to only 4,000 degrees Celsius, the electron begins to calm down and they find a more stable position on atoms. And after they recombine with these atoms, it releases a lot of light, a huge wave of light across everywhere in the universe. All atoms were created at the same time, basically, at this point. And created light, shining light everywhere in the universe. And that's this is the oldest light that we can see. This is the oldest light we can see. That's what we call the cosmic microwave background. That light that happened 370,000 years after the Big Bang, we are still seeing today as the cosmic microwave background. And how do we know that it happened everywhere in the universe? Is because when we first discovered it, all the same how is everything the same temperature here? 2.7 degrees Celsius. So it's really, really, really cold, basically. Well, to be specific, it's Kelvin, which is about negative 273 degrees Celsius, to be specific here. So negative 273 degrees Celsius is about how cold it is. So very, very, very cold. And even though you see some hot spots, right? There's some hot spots here that are red and some places that are yellow. Those places aren't actually that much warmer than the rest of the background. Those spots are actually only 0.00001 degrees Celsius warmer. So they aren't really that much hotter at all. It's just everything is the same temperature, basically. So that's how we know there's evidence that this recombination happened everywhere in the universe, because we look anywhere in the universe and we see the background. So that's when we know that's evidence that the Big Bang happened. Yeah. And afterwards, that's when stuff that we know begins to happen. Star formation begins to happen. We start to see galaxies, we start to see stars being made, we see planets. So that's star formation. So, all right. So, sure. I think this is really cool because this shows we call the basically just this is the catch up. Logarithmic picture of the universe. What we call it logarithmic is because the further and further you get away from the center, the further, so for example, the distance between here to here might be, let's say, 0.01 light years, right? But the distance between here to here might be 100 light years. And from here to here might be 10,000 light years. So as you get further and further away, you get further and further away a lot faster, basically. So this describes everything in our universe on a logarithmic scale. So all you have to know is the further and further you get it away, you get exponentially further and further away. So at the very center, we have our sun, right? We have Earth, we have our moon, we have Mars, Jupiter, Saturn, right? Everything that we see within us. We know a lot about these things. And then as we exit our solar system, this is the edge of our solar system, basically. We have a lot of stars, right? This is, stars within our own galaxy that we see, right? And then all those stars, if you notice, are being funneled into the Milky Way. This is our galaxy, right? That's the Milky Way. This is the section of the Milky Way that we can see. This is the section of Milky Way we can see. And then that's the Milky Way in general, right? And the Milky Way is also part of a collection of galaxies, what we call the local group. The local group is made out of, the Milky Way, the Andromeda Galaxy, Triangulum Galaxy, and a lot of other galaxies, right? We're all clustered together. And all of those galaxies are all in their own groups. And you keep on zooming in, you see those galaxies are part of their groups, and they form all their structures and stuff like that. So why it kind of looks like these branches is because all these branches are strings of galaxies that are all gravitationally bound to each other. They're being attracted to each other. So on the large scale, what the universe looks like is a bunch of branches through space, kind of. And the further and further you get, the more and more of these, it kind of just looks like static, right? It kind of looks fuzzy. because that's just, you're seeing much further and further into the universe. And eventually you don't see anything at all. That right here is the cosmic microwave background, CMB. That's the furthest we can't see any, there's no light from anywhere before this cosmic microwave background happened. So that's it. That's our universe, the observable universe. Everything is bound within this kind of bubble of the cosmic microwave background. There could be a lot of stuff beyond our observable universe, but we are needing to expand. And as things begin to expand, we can no longer
You're on mute.
Sorry, thank you. That's why when we say the Big Bang Theory, we still include the word theory, right? Because we aren't 100% sure. Everything is bound by this cosmic microwave background. We don't know much else before this because we don't have evidence of it. So it's completely possible that we're just 100% wrong about how the universe came to be, right? Because what if the universe is completely different outside of our bubble? What if there's like another bubble over here, right, of a other section of the universe that's just completely different from ours? We would have no idea. So that's why we call it a theory. It's a really good theory because it explains a lot about our universe and how things came to be, but it's still just a theory. And that's what is known as the horizon problem on this slide. Everything is bound by this horizon of the cosmic microwave background, and we cannot see beyond it. So yeah, there's a lot more stuff in cosmology because you're talking about some crazy stuff, right? You're talking about where did the universe come from? So there's stuff that I wanted to talk about, like dark energy and stuff, but that's gonna have to, you guys are gonna have to research that on your own time if you're interested. Because today, class, I'm gonna have to wrap it up. All right. So I hope you guys learned something about the universe, how we came to be, and where we are on the situation with cosmology and how much we know and how everything is just a theory. All right. So that was the end of today's class. I hope you guys enjoyed. I will see you guys next week.